Alright guys, for the new unit we're starting, which is going to deal with satellite and orbital motion, we need to understand a little bit more about gravity than we already do. So Newton, in addition to his 3 laws of motion, researched gravity a lot and came up with his law of universal gravitation. And he figured out 3 big things about it. First of all, gravity is an attractive force between any 2 objects with mass. Now, in order for that force to really be very large, at least one of the objects needs to be a very massive object. But technically you have a gravitational force between any 2 objects with mass. The second thing he noted was that the gravitational force is directly related to the mass of both the objects. Okay, so the bigger the masses, the bigger the force. And then the third thing, he noticed that there's an inverse square relationship to the distance between the objects. So the farther apart they are, the lower the gravitational force will be, and it's an inverse square relationship. So with all that, he came up with the following equation. Alright, so this equation shows exactly what we just talked about. It says that the force of gravity is equal to big G, which we'll talk about in just a second. It's the universal gravitation constant, times m1, the mass of the first object, times m2, the mass of the second object, divided by r squared, where r is the distance between the centers of masses of the 2 objects. So you see 2 different forms of the equation here. The one on the left is the vector form. So what we see is that f, g, and r have arrows over them showing that they're vectors. That negative sign tells me that the direction of the radius vector and the direction of the force vector are opposite in directions. So if an object was to the right of another object, the gravitational force would pull it back to the left. We're usually just going to care about the magnitude of that force, so we'll usually use the equation on the right. As I said, mass m1 and m2 are the masses of the 2 objects, but we do need to talk a little bit about g and r. Alright, so g is that universal gravitation constant, and Newton figured out that that value is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. And it's just the value that has to be put in there to make the force come out correct. Okay? And then r, as I said earlier, is the distance between the center of masses. So if that circle on the left represents object 1 and that circle on the right represents object 2, notice that r is not the distance between their closest edges, but the distance between the centers of the 2 circles. And that's important if you have large objects. Alright, so let's try an example problem. Alright, so let's say we want to know what is the gravitational force between an 80 kilogram person that's standing on the surface of the Earth and the Earth itself. Okay? So the circle there on the left represents the Earth and the little red dot represents the person. The mass 1 will be the person, 80 kilograms. Mass 2 will be the mass of the Earth, which is 5.97 times 10 to the 24th kilograms. And then the distance is going to be the distance between the person and the center of the Earth, not between the person and the surface of the Earth. So we are actually going to use the radius of the Earth itself as our distance, which is 6.37 times 10 to the 6th meters. So let's plug into our equation and see what we get. Alright, so we've plugged in our value of g, 6.67 times 10 to the negative 11th, times the mass of the person, 80 kilograms, times the mass of the Earth, 5.97 times 10 to the 24th kilograms. And we've divided by the radius of the Earth squared, and that comes out to 785 newtons, or approximately 800 newtons. And hopefully, at this point, some of you have realized there's a much easier way to work this problem, because the gravitational force between an object on the surface of a planet and the planet is known as the object's weight, which would just be m1g. So we could have easily just said 80 times 9.81 and gotten our 785 newtons. Okay? Or if we had used 10 for g, we would have gotten that 800 newton value. So remember, weight and on the surface of the Earth, the gravitational force on the surface of the Earth and weight are the same thing. So that definitely would have been an easier way to work that problem. But it does bring us to an important point. So if we wanted to determine little g, strength of gravitational field or acceleration due to gravity on a planet, we can take our 2 equations for gravitational force and set them equal to each other. And what we'll see is that m1, the mass of the object, cancels out. And so we're left with the acceleration due to gravity is big G times the mass of the planet divided by the radius of the planet squared. So let's try that for the Earth. So as expected, plug in the value of g, plug in the mass of the Earth, plug in the radius of the Earth, and solve, and we figure out that g is 9.81 meters per second squared. So what we've done is a lot of work to figure out something that you guys already knew, but now you know why it's equal to that. And what's powerful about this is, what if we wanted to know the acceleration due to gravity somewhere well above the surface of the Earth? Or what if we wanted to know the acceleration due to gravity on the surface of a different planet that had a different mass and a different radius? Using this equation will allow us to solve that. Let's do an example. So let's say we want to know what is the acceleration due to gravity on the International Space Station, which orbits the Earth approximately 400,000 meters above the surface. It actually gets closer to that than that sometimes and further away sometimes because it's an elliptical orbit, but we'll just use that as an approximate average value. So let's write out our givens. So when we do that, first of all, the mass of the Earth is 5.97 times 10 to the 24th kilograms. And then for our radius, now we have to do the distance from the space station to the center of the Earth. So it's actually going to be the radius of the Earth plus the altitude, the distance above the surface of the Earth. So when we add those together, we get 6.77 times 10 to the 6th meters. So let's plug that into our equation and figure out our value of g. So I've plugged in my values here, and what I see is the acceleration due to gravity on the International Space Station is actually about 8.69 meters per second squared, not much less than that on Earth. We think of that as being a weightless situation. It's not that there's actually no gravity. It's because of the orbital motion of the satellite that you feel weightless when you're making that orbit. But there is actually plenty of gravity acting on the International Space Station, which is actually what keeps the International Space Station in orbit around the planet. All right, one more thing to talk about today. So the last thing we're going to talk about today is another way to calculate gravitational potential energy. And what you'll see is that the equation looks very similar to the gravitational force equation that we just talked about. And the way you get from one to the other requires calculus. So we're not going to talk about it here, but those of you in calculus right now will probably be able to figure out the relationship there. So what you'll notice is that UG is actually always negative. And so that has a kind of funny meaning there. That tells us that as our r value, our distance, approaches infinity, as we get very, very far away, then the gravitational potential energy is going to approach zero, which is actually the maximum value. Okay, so the biggest value you're ever going to have for gravitational potential energy is zero, and anything closer than infinity, which of course everything is going to actually give you a negative value. And then as that r approaches zero, as the objects get very close together, the gravitational potential energy is going to approach a negative infinity, which will actually then be our minimum value. So it's kind of weird that these values are always going to be negative. Okay? We're not used to thinking of it that way, but that is how it works for gravitational potential energy. So now the last thing we're going to do is we're going to compare this equation to the old gravitational potential energy equation you guys know near the surface of the Earth, which is mgh. So let's say we took our 80 kilogram person and put him 100 meters above the surface of the Earth. If I had asked you guys to calculate the potential energy of the person Earth system, you would have probably plugged into mgh. You would have done 80 times 9.81 times 100 and rounded to three significant figures. That comes out to 78,500 joules. Well, let's test our new equation and let's see if that works. At a height of 0 from the Earth's surface, the radius there is going to be 6.37 times 10 to the 6th meters. Okay? And at a height of 100 meters above the surface, it's going to be that number plus 100, which comes out to 6.3701 times 10 to the 6th meters. And so what I'm going to do is use our new equation to calculate the potential energy at both of those spots. All right, so I plugged in the numbers for 100 meters above the surface of the Earth and got a value of negative 5,000,850,850 joules. So that'd be negative 5,850,850 joules. Okay. Then I plugged in the values for at the Earth's surface, and I got negative 5,929,356 joules. And so we see that at 100 meters above the surface, we have more potential energy than we do at the surface. Now, if we want to figure out a relative to the surface of the Earth, calling the surface of the Earth 0, what I'm going to do is take the potential energy at 100 meters above the surface and subtract the potential energy at the surface, and that should give us our relative potential energy. And so what I see there when I subtract those two values is once again rounded to three significant figures. It comes out to 78,500 joules. So our two answers agree. And of course for this problem, the way we did it up top is going to be much easier than what we did down here at the bottom. Typically you're going to use this type of equation if you want to know the potential energy between a satellite and the Earth, or the potential energy between the Moon and the Earth, and the Moon actually is a natural satellite of the Earth, or the potential energy between the Sun and the Earth, dealing with planets, dealing with orbits, and things like that. But that's how the equation works. All right, guys, that's all we're going to talk about today. I've got a few problems for you to try, and we'll discuss them at the beginning of class tomorrow.